um, Math 26, we go over section 4.5 today. Okay, 4.5. This talks about the dimension of a vector space. Dimension of a vector space. You know what a vector space is, right? And we are going to find the dimension or learn how to calculate or find the dimension of a vector space in this section. So the first thing I recall here, we usually let H be a subspace because we're going to use this subspace of Rn. Okay, so a basis for H is linearly independent set of vectors, right? Vectors that spans H. That's how we define the basis. We did that before. Okay, the dimension of this subspace H is calculated by finding the number of vectors in any basis of H or for H. And before we proceed with this, if V, the subspace V, is spanned by a finite set, then V is called finite dimensional vector space. Again, the dimension, we use dim to abbreviate dimensions. So the dimension of V can be found, as I showed you about the subspace, is the number of vectors in a basis for V. Okay, I mentioned this earlier, but I did it for V for H. So if we are asked you what's the dimension of the zero. So zero means the zero space. This is the zero space. Okay. How many vectors are in the zero space? No vectors. No vectors. So this means the dimension of the zero space is really zero. How about the dimension of Rn? So how many vectors do you need to form a basis for Rn? We need n vectors. So yn, because we need n vectors to form a basis for this vector space. How about the dimension of the polynomial space? Pn, polynomial space. So this is polynomial. Well, how do we know? Well, remember, if you have quadratic, what was the basis? 1t squared, remember? So you have one more vector or element in there. So it's going to be always n plus 1. And if V is not spanned by a finite set, we call it the infinite dimensional space. Okay, so we're going to see a lot of examples today how to calculate the dimensions of a vector space, but let's introduce a theorem first. If a vector space, VS means vector space V, has a basis B with vectors B1 all the way to Bn, okay, then any set in V containing more than n vectors must be linearly dependent. Not independent, remember, it's dependent. So again, it has, because this vector space has this as a basis, so there's n vectors here, right? N vectors. And so what happened, then any set in V containing more than n vectors is going to be linearly dependent. How does that work? This works means most likely one of the vectors is a multiple of the other, or one of the vectors can be written as a linear combination of the other vectors. That's what the theorem is saying. Is that okay? To support this theorem, we introduce another theorem, good to know, and we build on those informations when we start working with examples. If a vector space V has a basis of n vectors, then every basis of V must consist of exactly n vectors, right? Let's start with some examples. Let V1 1 3 4, that's the first vector, V2 1 0 negative 1, and H is the span of these two vectors. We need to find the dimension. Find dim means dimension of H here. How do you find the dimension? Okay. For now, for the meantime, what we can do, we can by inspection, we say, if you look at these two vectors, can you tell if one of them is a multiple of the other? I don't see that. So I don't see that V1 is multiple of V2 or V2 is a multiple of V1. That's by inspection. Then I'll show you later today what can be another way to work on this. So that shows if they are not multiple of each other. So what does that mean? So V1, V2 are linearly independent vectors, right? So they form the basis for H. And since they're not multiple, since they are not multiple of each other, okay, not multiple of each other. So again, they are linearly independent because they're not multiple of each other, and hence the basis. So this means this set V1, V2 forms a basis for the subspace. Then the dimension of H is the number of linearly independent vectors here, V1 and V2, so two vectors. So the dimension is 2. Next example. find the dimension of the subspace H where so someone is asking why it's 2. So we defined, if we scroll back up, the dimensions of a vector space, as you can see here, is the number of vectors in any basis, right? The dimension is the number of vectors in any basis. So here, what I did here, I proved that these 2 vectors form a basis for the subspace H. And since there's only 2 vectors, that means the dimension is 2, because that's the number of vectors. Hope that explains it. So now we need to find the dimension of the vector of the subspace H, where H is 4s, -3s, -t, such that s and t in R means they are real numbers. So what do? We take this in parametric form, is called, by splitting this into 4s, -3s, and 0, plus 0, 0, -t. And we can pull s out, factor out 4, -3, 0, factor a t out, 0, 0, -1. Now what we do, we'll look at these 2 vectors. We let, this is v1, this is v2. By inspection, are they multiple of each other? No. So we say v1, v2 are linearly independent. So vectors, set of vectors. This means they form a basis for H. Since they form a basis for H, then the dimension of H is exactly 2. So H here is the span of v1, v2. Same for 3a plus 6b minus c, 6a minus 2b minus 2c, -9a plus 5b plus 3c, -3a plus b plus c, where a, b, c, d are real numbers. So now what I want you to do is, I want you to work on this as groups. So here, what do we do? Again, we write in a parametric form, so we can take a out, here a out, and what is left? 3, 6, -9, -3, plus b, 6, -2, 5, 1, plus c, -1, -2, 3, 1. Okay, so this is v1, this is v2, v3. So v1, v2, v3. You can look at these 3 vectors and see if, what do we see? Oh, I see. Note that v1 is -3, v3. Right? So this set now, v1, v2, v3, is not linearly independent set. So what do? We remove v3 from the set by, we call it the spanning set theorem. So this means H would be spanned by only two vectors, v1 and v2. So the dimension of that would be simply 2, not 3. Any questions about this? So this was by inspection. How about if we look at another one, another set, say A plus 2B minus 3D, 5A plus 10C minus 5D, and B minus C minus D, such that A, B, C, D are all real numbers taken from the real numbers. Find the dimension of H. Of this subspace. So what do we do here? Of course, you can write H in, factor A out, and you get 150 plus B out 201, then C out, and then 0, 10, -1, and D out -3, -5, -1. Okay. So maybe you're going to sit by inspection, look at them and see which one is a multiple of the other and things like that. But what's another way to do this, to check? We can write these, form a matrix of these vectors. We can form a matrix of these vectors and write these vectors as what? Write this in a reduced row echelon form. Reduced row echelon form. So do that, you can multiply -5 row 1, add it to row 2. So what do we get? 1, 2, 0, -3 stays the same. -5 times the first one is -5, added to this is 0. -10, 10, and -5 times that's 15, and that's another 10. Keep the last row the same. Now I clean the first column. Now I want to get this to be 1, so I do -110 row 2. 1, 2, 0, -3 stays the same. 0, 1, -1, -1, 0, 1, -1, -1. I can clean this number here by multiplying row 2 added to row 3. So that will become 0, 0, 0. Right? And now I want to clean what? So I want to clean this number here. So I take row 2 multiplied by -2 added to row 1. Let's see what we get. We get 1, 0, 2, -1. This stays the same. And all the zeros stay the same. Now, if you look at these, can you find any of these vectors as a linear combination of the other vectors? So this is V1, this is V2, this is V3, this is V4, So notice V1 and V2, they have nothing to do with each other. They're not like multiples or can be written as a linear combination of other ones. But if I look at V3, V3 is basically 2 times V1 and then minus V2. So that would give me V3, right? How about V4? Can I write V4 as a linear combination of other vectors? Well, yeah, there's a negative 1 on the top. So negative V1, and there's negative 1 again here. That's minus V2. Oh, wow. So I have 2 vectors that can be written as a linear combination of the other vectors. So those are kind of like redundant vectors. We remove them. So that will leave only 2 vectors left, V1 and V2. Okay, so this means H can be spanned with V1 and V2 only. And in this case, since H is spanned this, the dimension of H is 2. So now we introduce another theorem. So the theorem said, if H is a subspace of a finite vector space V, then any linearly independent set in H, in the subspace H, can be expanded. So it can be expanded to a basis for H, and always the dimension of H is always less than or equal to the dimension of V. I'm not gonna show you the official proof or the formal proof of it, but I want to talk a little bit about it, not just state it out. So let's say this is a vector space V, and there is a subspace H sitting inside it. Okay, if we take set S in H, so set H S of vectors, say, this is S in H, where S contains V1, V2 all the way to VP. Okay, so this is the set. S contains V1, V2 all the way to VP. So what do we do in this case? What happened to this S? If S spans H, then done. Why? Because it's a basis. So linearly independent vectors form a basis, then we're done. If S does not span H, so what we do in this case, if you remember the spanning set theorem as we did earlier today, we showed you about the redundancy of vectors, how we remove the vectors. So that theorem tells us you can remove the vectors if one vector is a multiple of the other, or if a vector can be written as a linear combination of other vectors. We remove them. That was the spanning theorem. In mathematics, the opposite way we call the counter positive, like we call the counter is the counterpart of the spanning set theorem. So the counterpart of the spanning set theorem means if S does not span this, we can add more vectors. We add more vectors to S. Okay, to get it to the point that S is the span of H. Okay, is the span of H. So what do we add then in this case? Well, we can take S and add union, means combined with some other vector V sub p plus 1. And this vector must be linearly independent with all the other vectors of S. So then the new S, let me call it new S, has vectors v1, v2 all the way to vp comma vp plus 1. So assuming this is gonna span, so this one spans H. But how about if it doesn't? Even after adding one vector, you can add the next one, next, and the following, until you get to the point that that set spans H. And that's what they meant in the theorem. In the theorem, that's what they meant by expanded. So expanding, that's what this means. Okay. So in summary, I can keep adding vectors to this set S until I get it spans H, and then this set of vectors is a set of linearly independent vectors. Hence, it's a basis for H, and then that will help us to find the dimension of H. So now another part to the theorem, it says that the dimension of the subspace H is less than or equal to the dimension of the vector space V. This is obvious because all the vectors in H are included with V, if that makes sense, right? So this is obvious, true, since all vectors in H are also in V. So we're not going to pass the number of vectors. The number of vectors in H is not going to pass the number of vectors in V. So that's what this theorem says. Now we have another theorem to talk about. The next theorem says, let V be a n-dimensional vector space. Okay. Let V be any dimensional vector space. Any linearly independent set of exactly n elements in V is automatically a basis for V. So any set of exactly n elements that spans V is automatically a basis for V. So what this is saying, it's kind of like backwards of what we just were doing. This is saying if you have any linearly independent set of exactly n vectors, n elements, like n vectors in V, if that set has exactly n elements, linearly independent vectors or elements in V, and V is n-dimensional vector space, then this proves automatically, the theorem said this automatically means that this set of those n vectors is a basis for V. Another way to say it, or you can say any set of exactly n elements that spans V is automatically a basis for V. Isn't that obvious? So if you have n linearly independent set of vectors in V, and V is of n dimensional, automatically means that set of vectors is a basis for V. And the next thing I want to talk about, the dimensions of the null space of A and the column space of A. So we know that the pivot, we call them pivot columns in previous sections, of matrix A form a basis for A. Okay, so the pivot columns of A form a basis for A. Therefore, the dimension of the column space of A is the number of pivot columns in A. That's how we find the dimension of the column space of A. It's basically the number of pivot columns in A. Also, if you go back, I believe in section 4.2, we learned that to find a spanning set, we could or we would have a vector for each free variable. So if you have 5 free variables, you have to have 5 vectors. Therefore, we say that the dimension of the null space of A equals the number of free variables in A. So it will be 1 vector per free variable, right? Now, what we can do, we can look at an example. Let A 1 0 0 4 0 0 2 1 0 1 negative 3 1. Find the dimensions of the null space of A and the column space of A. So right away, notice something about this matrix. It's already in row reduced echelon form to make it easier. We don't have to do all these computational stuff. So first, which we can find, if you like, the dimension of the null space. Okay. So how do you find the dimensions of the null space? We need to find the number of free variables, right? Where are the pivots? 1, 2, 3 pivots. So we have those 3 pivots, as you can see. So what do? Now, So here we have 3 pivot columns, right? And this tells you what? This is a free variable here. Right? So to find the dimension of the null space of A, it's the number of the free variables. So in this case, it's only 1. Right? And the dimension of the column space of A is the number of pivot columns, right? And we told you it's 3 pivot columns. So just a quick note, a side note, if you add them up here, 1 plus you get 4, that's the total number of four vectors, as you can see in the given matrix, given matrix here. So any questions about this one? Another example. 1 0 0 negative 2 6 0 0 8 3. This should be easy. Try it on your own for a couple minutes. So here, how many pivot columns do we have? We have 1, 2, 3 pivots. So 3 pivot columns. This means the dimension of the column space is 3. And I don't see any free variables, right? No free variables. Each column had a pivot. So the dimension of the null space of A is simply 0. How about if we give you another example? A equals 1 0 0 0 negative 8 1 0 0 7 3 0 0 0 negative 3 8 0, then negative 3 6 1 0. How about this? We need to find the dimension of the null space of A and the dimension of the column space of A. Notice it's A is in echelon form. So, and it has a pivot here, a pivot there, a pivot here. So there are 3 pivots. So 3 pivot columns. And since there are 3 pivot columns, the dimension of the column space is 3. Now these two, this one here and this one, they have free variables, right? So 2 columns with no pivots. So this means 2 free variables, means the dimension of this is 2. And notice if you add them up, 2 plus 3 is 5. And look, we have 5 total, 5 number of 5 numbers of vectors in A. Next one, 1 negative 1 0, negative 3 2 2, negative 4 6, negative 5 2 3 0, and the last one is 0 1 2. You are required to find the dimension of the null space of A and the dimension of the column space of A. Try them. Try this one. So the difference between this example and the previous examples, the other ones I already gave it to you in reduced row echelon form or in the echelon form. This one is not. So you have to do operations, like row operations, to do it. I can give you the answer after the operations. I got 1 0 0, and then if you like us to do it, we can do it, but it should be easy for everyone. 0 1 0, negative 10 negative 2 1, third column, fourth column, negative 13, negative 5, negative 10, and then negative 3, negative 1, negative 4. That's what we have. Now, how many pivots are there? This is a pivot. This is a pivot. This is a pivot. 3 pivots. So 3 pivots means 3 pivot columns means the dimension of the column space is 3. That will leave this and this with 2 free variables. So that tells us the dimension of the null space is 2. Dimension of the null space is 2.